This is our report on a telesurgery robot and how feedback design control systems can be implemented within. I'm Carter.
I'm Robert.
And I'm James.
Telesurgery robots are complex machines which interface a surgeon-side subsystem with a patient-side subsystem to successfully perform surgery. Typically, the surgeon sends instructions through a console on the surgeon-side subsystem, and two robotic arms in the patient-side subsystem respond to the console commands. One robotic arm operates medical equipment, and the other robotic arm operates a camera, which feeds video signals back to the surgeon-side subsystem. Together, the two subsystems create a device which enables surgeons to remotely perform operations around the world. Additionally, telesurgery robots create opportunities for patients to get correct care even if local surgeons are unable to perform an operation that would require a specific set of skills. Telesurgery robots need to be designed as safety critical systems because system failure can lead to serious patient injury or death. As such, telesurgery robots need to operate on secure and reliable networks to ensure system reliability. At the most basic level, telesurgery robots work by adjusting the voltage to a motor and adjusting the angle of the robotic arm. Feedback is needed in the system because the robot needs to keep adjusting the angle of the arm until the angle matches the surgeon's input. The system needs to be stable because the robotic arm needs to reach and stay at the angle chosen by the surgeon. Thus, feedback is critical to the telesurgery robot because precise location of the robotic arm needs to be maintained so that the user input can adjust the robotic arm accordingly during one operation.
These are some of the transfer functions that we use to model our plant diagram. This is the fully combined block diagram of our plant and simplified with these constants that we found worked well with our plant. Gave us the final transfer function, theta in radians over VA of S in volts.
So the analysis of the system, we will first look into disturbance, and we expect there to be minimal to no disturbances experienced since the telerobotic surgery will happen in a medical room where most possible disturbances will be removed. The second thing we look into is reference input. Due to the nature of telesurgery equipment, we need very little error in order to avoid mistakes. For this purpose, we will use a unit step input so that if a PI controller is used, we will have a type 1 system and zero error. The last thing we look into is BIBO stability. Since our open loop transfer function is a third order system, and for realistic applications we will have all positive constants, there will be no right hand plane poles. In addition, since our transfer function is proper, we can apply the Routh-Hurwitz test for stability. Here we can see the Routh-Hurwitz set up. When plugging in our constants used from earlier, the first column used to determine stability is as such. From the Routh-Hurwitz test, we see that all of the columns are positive. This means that all of the poles of the transfer function lie within the left half plane, and as such, we can conclude that our transfer function is BIBO stable.
We chose 3 different specifications for our system: percent overshoot, rise time, and steady state error. Percent overshoot is chosen because we want our system to have extremely precise movements. We do not want the motor to rotate further than our expected angle. The rise time will allow the motor to reach the angle at a fast time so surgery can be swift and safe. And then steady state error was chosen to be minimized so that the arm can be rotated into the correct position for precise cuts to occur. We need to make sure that the arm stabilizes at the exact right spot. To meet our design goals, we'd like to achieve a rise time of under 1 second, a steady state error of 0, and a percent overshoot under 10%.
In our design considerations, we chose to use a PI controller along with a step input, allowing us to reach 0 steady state error. We were able to use SISO tool to add the PI controller 0 and manipulate its location along with multiplying by a proportional constant K in order to give us a small rise time along with a small percent overshoot that fit within our design specifications. This is our final transfer function included with the PID controller used in Simulink.
For verification and iteration, We chose to change these zero values until we were able to reach our final controller. As you can see, when plugged into Simulink, our rise time actually reaches down to 0.864 seconds, which is under our goal of 1 second. Our percent overshoot is equal to 7.19%, which is under our goal of 10%, and we were able to reach a steady state error of 0, which also fits our design requirement.
We next chose to examine the robustness of our system. Our phase margin can be seen as 20.3 degrees, and our gain margin can be seen as 15.1 decibels. We have a crossover frequency of just about 2.01 radians a second. The time delay, according to our equation, TD is equal to the phase margin over the crossover frequency, is equal to 0.176 seconds. Shown here in the Simulink step is the Simulink step response with the maximum time delay. This proves that our system can remain stable with any time delay less than 0.176 seconds.
In conclusion, through the use of SisoTool and Simulink, we implemented a PI controller that allowed us to adjust our closed-loop response to fit our specifications, decreasing rise time, percent OS, and the steady-state error. In addition, having a maximum time delay of 0.176 seconds, our plant system had some room for time delay error, which likely would happen in a case like ours, where signals are being transferred across long distances.